Okay, so we are starting again on 107. We're going to be finishing up chapter 7, and then we'll be doing the exam next week, right? Fantastic. Okay, and so we are going to be oxidation reduction. When we are being oxidized, what is that going to involve? Yeah, it doesn't always involve oxygen, but in physiological processes, it usually involves oxygen. Oxidation means that electrons are being taken away, right? What's reduction then mean? Yeah, you're gaining electrons in the case of a reduction, okay? Are you ever going to have one without the other? Can you have a murder without a victim? No? Can you have a murder without a murderer? No. And so, if you have an oxidation and a reduction, one is taking from the other, right? And so you have to have a reduction if you have an oxidation, and vice versa. Okay, so it's always going to involve the loss of an electrons. In biological processes, it can often be traced by looking at it as the addition of an oxygen, in which case the other thing that gained the oxygen got oxidized. Okay. You can also see it as the loss of hydrogen atoms. If something loses hydrogen atoms, it is very typically going to mean it's been oxidized. Okay. The reverse of those trends would be reduction. So loss of oxygens, gaining of hydrogens, those are typically hallmarks of reduction when we're looking in biological processes. Okay. The correct definition of it, though, is gaining electrons. Right? Okay, so this right here is actually an example of a oxidation reduction reaction. And so here we have iron reacting with sulfur. And so again, the mass of the product is always going to be same as the mass of the reactants that combine together, right? Anybody know what iron forms of iron sulfide often are? These are very typically the things you find for like scaling on iron pipes, but they're also things you'd find for like, anybody ever been to a hot springs? Yeah. So have you ever seen something that looked a lot like that, right? Yeah. Very common to see around hot springs. There is a form of iron with sulfur that is actually called fool's gold. Anybody ever seen that before? Yeah. And it looks like gold, but it's much harder. Okay. So the law of conservation of mass indicates that in ordinary chemical reaction, matter cannot be created or destroyed. There'll be no overall change in mass. Does that mean that the mass of the product is the same as the mass of one of the reactants? No, it's the mass of the total reactants, right? That reacted to form it. Okay. It's a misconception. It's very common in students starting to learn this, is they try to go, I have 10 grams of iron, so I must have 10 grams of the iron sulfide. That has to not be true, doesn't it? Because you've added sulfides to the iron sulfide, haven't you? So there's no way that you can have the same mass of iron and iron sulfide. That would not be true. It's the iron plus the sulfur gives you the mass of the iron sulfide, right? So the mass of the products is going to be equal to mass of reactants. This is actually tarnish. This is silver with sulfur. And so silver will react with sulfur. And that makes that black gunky stuff that you see on silverware, like very old sets of silverware or silver jewelry. Anybody ever seen that before? No? Yeah? That actually means it's not silver. That's not very pure silver, yeah. Yeah, that would actually likely be copper. Yeah. But it could be a few different alloys, but most likely copper. Silver actually typically will tarnish with this color. See that real deep black color? Almost can't see it because it's so dark, right? That actually is the color that silver sulfide turns into. And that's a pretty good marker of it's very pure silver, by the way. It'll do it very slowly, and so you'd have to see a set of silverware. Typically 40, 50 years, you'd see a little. Okay? And it'd mostly be in like the recesses. Okay, so this right here is actually the reactants in the product right there. And this is how many atoms go into that reaction. And so we see that if we have 2 atoms of silver, 1 atom of sulfur, that would be 1 silver sulfide, right? And then if we have 200 atoms, then that would be 100 atoms of the other and 100 of the silver sulfide, right? Everybody see that? They scale proportionally. Okay. And so this is the moles. Again, moles are just packages of atoms, right? And so if we have 2 moles of silver, 1 mole of sulfide, that will give us 1 mole of silver sulfide. Okay, fantastic. This is how the masses work out for this. And so we see the total mass of reactants has to be equal to the total mass of products. Again, the reactants are what are actually going to be consumed in this reaction. You guys will find out in a bit. Well, you guys that have had lab, you already kind of have an idea of why I keep saying that. The people that haven't had lab, we will find out soon. Okay? By the way, does anybody know what day it was yesterday?
Mole day.
It was mole day. And we learned about moles very, very similar time as mole day, didn't we? Yeah. Yay. Okay. And so again, this is the silver sulfide reaction, and you can write it out as such. Now, let's talk about the mole-to-mole factor. This is going to be the ratio of the moles for any 2 substances in an equation. It's just the ratio you would need if you were to trying to make it, right? It's the same sort of thing as saying I need 4 cups of flour in this cake. How many cups of flour do I need if I make 3 cakes? Nobody? Oh, wow. Okay, so I need 4 cups of flour to make a cake. If I need to make 3 cakes, how many cups of flour do I need? 12. Exactly. It's the same thing, isn't it? Because these are just recipes to make this, isn't it? Just like if you have 4 cups of flour, 2 cups of sugar, you can make, I think that makes bread actually. But, yeah. I think I need more sugar to make a cake, don't I? Yeah. Anyways. So these are again just the mole-to-mole factors or mole-to-mole ratios. Okay. Usually referred to as mole ratios, but your book calls them mole-to-mole factors, so I'm going to stay consistent with your book. Okay. Okay. So again, these are equations. These are just ratios, like you would use for any recipe. So let's consider this following equation. What would be the mole-to-mole factor for H2 and N2? So we're going to look at the coefficients in front of each of those, right? And we're going to plug those coefficients in. So what's the coefficient for N2? That's 1. The coefficient's the thing in front of it. Okay? Notice I had said for N2, right?
So it would be a 1 if there's nothing there.
Exactly.
Okay.
Yeah. It being there means it has to exist, so
Okay.
1.
Yeah.
Yeah. And you don't need a number because it exists. So, and then for the H2, that would be 3. Very good. And so for 1 mole of N2, you'd have how many moles of H2? 1 mole of N2, we'd have 3 moles of H2, right? I just took the coefficients. 1 mole of N2, we have to have 3 moles of O2. Just like saying for 1 cake, I have to have 3 cups of flour, right? Okay. Just what we're doing. So how about the mole-to-mole factor for NH3 and H2?
3 moles.
Yep, we have 3 moles of H2, right? And then how many moles of NH3?
3
Where's the NH3?
With NH3, there's a 3 next. Oh, so 1. Wait, where are we? Oh, are we on B?
You're on B.
You're on B, is what we're trying to solve right now.
Oh, okay.
But we look up at this equation here, and we're trying to do the moles of NH2.
That's 2 for NH3.
Yep, 2 for NH3. And then the moles of H2. And that one's 3. So those would be 2 moles of NH3 over 3 moles of H2. Yeah. Which is that one right there. Okay. So how many moles of Fe2O3 can form from 6 moles of O2? All right, so let's look at these, how we can actually use these to predict things. Okay? And so we have this recipe, right? And so I have 6 moles of O2. How many of those products can I form? Well, I can use that mole to mole ratio. I put what I want to go into on top. That's 2 Fe2O3, right? And then on bottom, I'm going to take what I want to go out of, which is the O2s.
Wait, can you explain that? I'm sorry, I'm just kind of confused.
So again, it is just like saying cups
Okay.
and cake.
Okay.
And so I have a recipe here that tells me 3 cups make 2 cakes, right?
You don't do anything with the 4FE.
No, I don't need that because it's not a limiting factor here. It's not something I am going to be stopped by. I'm trying to figure out, that would be like saying how much flour do you need to make your cakes? And going, I wonder how much sugar I need.
So
It's the other ingredient.
How do we know just to look at the 3 and then the O2?
Because
it
you're
has
looking
the
at the specific ingredient that's
Yeah.
being asked for.
Okay.
Yeah, yeah. Now, if it said, look, how many moles of Fe do you need? That would be, we'd have to look at Fe.
So you put the reactant on top and then whatever it needs on the bottom?
We put what we are starting in. We have 6 moles of O2. That's what we're given. So we have to put that on the bottom so we can get rid of it.
Okay.
Okay?
Yeah.
Because we're going from O2 into Fe2O3. Look at the question again. How many moles of Fe2O3 can form? We're being asked to go into Fe2O3 from 6 moles of O2. We're being asked to go from that into the other. Okay. Okay, so we're going to take the 6 moles of O2, we're going to multiply it by the 2 moles of Fe2O3 and divide by the 3 moles of O2, which is that right there. That's going to give us the number of moles we could produce of Fe2O3. Okay? Okay. All right, so that's that mole to mole ratio. It's not going to get used right away, by the way. This is just that Q&A if you ever want to ask questions. Okay. All right. We'll have another pop up in just a bit. Okay, so how many moles of Fe are needed for the reaction of 12 moles of O2? I should have. Yeah, okay. It's doing what it's supposed to.
There's no timer?
Nope, no timer.
Okay.
So you guys can join and answer and do what needs to be done. Yep.
Yeah, just read it first.
Okay,
That's why we used it and practiced
write
it
that
first.
down.
This is the equation,
Oh, okay.
in case you forgot the equation. Yeah.
I was like,
Yeah. I broke down and ended up paying them, so the next ones I'll actually have the pictures put in.
you paid for it?
Yeah.
We appreciate your sacrifice.
Yeah, it was. Hey. Okay. There you go. Okay. Yeah, in the long run, it's going to be tens of thousands of dollars.
The longer you teach.
Yeah. Because professors teach forever, right?
I'll be doing this at work tonight.
Good. Okay. Let's go ahead and move on. Okay, so go ahead and try to answer here. Yeah, for the educators plan, it's $7 per month.
A month? It's
Yeah.
84 bucks a year.
It is. Yeah,
So you're not going to spend tens of thousands, but it's probably,
yeah.
I mean, it depends on how long you
Well, if you compound the money, because I would have normally saved that money, and especially if you use my compounding, because I typically make somewhere between 20% and 150% interest every year.
So you would have to teach 119 years to hit 10,000.
No. I make 20% to 150% interest off of my money every year
Same.
because I'm a really good investor.
With what I invest, I set about 18. Honestly, it's about 12 to 18. 18's a high year.
This year was 180%.
Man,
Yeah.
I got stocks, like in Publix, I have a Publix stock.
Mhm.
A lot of like nerd stuff. I sell like, the other
Me
day
too.
my wife's like, what did you just sell? I'm like, I sold 5 childhood Pokemon cards for $2,000.
That's funny. Yeah, I mostly invest in like tech sector stuff because I
Yeah.
understand it well.
I do sports. That's my
I swear to God, it is
Okay,
always
folks.
it is always such a shock to me whenever I'm in class. I hear someone talking and the words "my wife" or "my child" or something comes out of their mouth because I'm like, we're in school. Why do you have? And then I remember we're all legal adults in this, and
Mm-hmm.
some people already do have that stuff.
That is true.
By the way, Professor Gothard was just as surprised that Legos were magnetic also.
Really?
Yeah, we had that conversation. She's like, no way. I'm
That
going to
is
have to ask him about that.
Points does this take on
Legos are
if
magnetic.
we don't get one of these?
I'm not currently applying any penalties for getting them wrong.
Okay.
Like if we were just like every time we're doing this, nobody's getting it right and everybody's just randomly selecting junk, then I'd start penalizing people. But no, everybody is actually giving efforts and trying. And that's what I really want to see. Yeah. Yeah. Yeah, so it's the 16 moles of iron. And again, if we go back to the equation, we have how many moles of iron are needed for the reaction of 12 moles of oxygen. And so what we're going to do here is we're going to put up a ratio of oxygen to iron. And so if we create that ratio is going to be 4 to 3, right? 4 moles of iron from here per 3 moles of oxygen. And so we need to get rid of the oxygen, so we're going to be using that one right there. And we're going into moles of iron. Okay, so we take the 12 moles of oxygen, we multiply it by that 4 moles of iron over 3 moles of O2, and that's going to give us the 16 moles of Fe. Okay. By the way, here's an interesting little factoid for you to make it help you stick. Anybody ever seen welding before?
Yeah.
Yeah, so that's welding, isn't it? Okay. By the way, does anybody know why it's a full mask like that and the person's all covered up?
Because those sparks.
Not the sparks, actually.
Gas and the metal fragments, right?
It's the sheer heat and light of it will actually cause like drastic sunburn to you. Yeah. And if you don't have the mask on, even if you're perfect and don't get any sparks on you or anything, you will have like your eyes will feel like they're sandpaper. Yeah, and it can actually do long-term damage if you do a lot.
That's why welders are always so tan.
Yeah, and that's why they always wear like full body protection. Yeah, it's not actually the sparks. Like the sparks don't hurt your arms that much. They go off pretty quick.
It's like little mosquito bites here and there.
Yeah, and they don't hurt you long-term much either. It's the sheer exposure to all that light, all that heat. Yeah. So, how do you know when a acetylene torch is working properly? There's a modulator in it, right? Why is that? Because you got to get that mole ratio perfect. That produces the best heat, right? If you mess up and don't have enough oxygen, you get this big flame, right? That has very little heat. Yeah, too much oxygen, it starts going out, and you start getting a flame that's like barely flickering. Yeah.
2-inch flames. Like,
Yeah. And that's what you're doing. You're actually modulating the mole ratio.
I guess science isn't the world.
I know, it's everywhere, right? Can't get away from it. Okay, so we're going to go ahead and talk about mass calculations now. So given a balanced chemical equation, we can actually convert the mass of one substance, A, to a substance B. First, we can use the converting the mass of the substance A to moles and using the molar mass of that first substance. Okay. Once we're in moles, we can actually take those mole ratios and we can get the moles of any other component of that equation, right? And then we can take the moles of that second substance, substance B, convert it back into grams. Okay? And so we can take the three steps we've been doing over and over and over here, and we can combine them together. And that gives you the ability to predict how much you should make if you put two things together. Gives you the ability to predict if you have something that came out, how much did you start with, etc. Okay? This is actually how they do most of that stuff where it's like, this had so much amount of cocaine this person snorted. They're not getting cocaine out of the person. That's not what comes out. Okay? They're getting a byproduct from the cocaine that comes out, and then they're doing these calculations to go backwards. Okay? Okay, so let's talk about an example. Suppose we want to determine the mass grams of ammonia that can be produced from 32 grams of N2 in this following equation. So right here we have a reaction. So what we're going to do is we're going to convert into the grams there into moles. Once we're in moles, we can use that in this reaction to get any other component of this reaction back out, can't we? That's just the mole to mole ratio. And then we're going to take those moles, we'll convert it back into grams because we're asked to give a number of grams, right?
Yeah.
Okay. Okay. This right here is your handy dandy drawing to help you visualize this in case you need something to visualize it with. Okay. So again, we have went through what do we have, what do we need, and we've traced a path to get there, haven't we? Okay. Now we're going to generate all the conversion factors we're going to need for this. So we need the molar mass of N2. We look up at our periodic table. We look at that number on the periodic table for nitrogen. We multiply that number by 2, right? And that gives us 28.0 grams of N2 for 1 mole of N2, doesn't it? Okay. And so we write out the equality, we write out the ratio. You don't actually have to do all those steps. That's actually just to help you because that's what's been done over and over in your book.
Wait, so you take the mass of N and multiply by what?
So it's N2.
Because it's in, okay.
There's 2 nitrogens. Yeah. Okay. So this right here is what we're doing for NH3 as well. We look up the periodic table for nitrogen. Then we add 3 hydrogens to that. Yep. And so we end up, if we don't round off the end of it, at 17.04 grams. Okay, so 17.04 grams of NH3 equals 1 mole of NH3. Okay. Now the next thing we're going to do is we're going to take and get the mole ratio here. So there's 1 mole of N2 would give us 2 moles of NH3, wouldn't it? Okay.
So
1 mole of N2 would give us 2 moles of NH3.
Mm-hmm. And that's because there's a 1
nitrogens on each
to
side.
2 ratio.
wait,
Yeah.
so okay. Where are you like dividing? What are all these like equations? I'm so lost. So
These are just conversion factors. We're stating these as conversion factors.
okay, so the 28.02 is the answer to what now?
Okay, so I'm just getting together the things I'm going to need to do this problem. And the things I need to do this problem are the molar mass of N2,
Okay.
the molar mass of NH3, and I need the mole ratio. This is the molar mass of N2, the molar mass of NH3, and the mole ratio of the 2. Okay.
So for the NH3,
Mm-hmm.
do you get the N mass and multiply? Like I don't know how to do that.
You take nitrogen and then you add 3 hydrogen because it's H3, so it's 3 hydrogen. Nitrogen
Okay.
is 14, and that's 17. That's how we got 17.04 grams. And that is 1 mole of nitrogen.
So, anyways, I'm gonna keep going on, and that's something that we did like 6 problems back a while ago on.
Okay.
So,
One question.
okay, uh-huh.
So on that last one, is there ever, would you ask us if we need, like, how would we balance it after that? Like at the bottom where I would need 6 hydrogen, and
Yeah, you might have to balance these reactions first,
Okay.
but likely not just because of time constraints. That's a
Okay.
lot of layers to put into one problem.
That's what was.
Yeah.
Okay.
But yes, you may have to balance these. In this case, this is actually a balanced reaction.
Yeah.
Yeah.
Sorry,
Just
I didn't-
no, you're good. Okay, so we have the 32 grams of N2 here. That's right there. And right here, we're going to use that molar mass ratio. We need to get rid of grams of N2, so that goes on bottom. We're going to want to go into moles of N2 because moles are the only thing we can go from one side to the other on this for. Okay? Because moles are literally a number of atoms, right? And that's what all these equations are, numbers of atoms. Okay? Okay, so we're now in moles of N2. So we need to use the mole to mole ratio. We need to get rid of moles of N2. We need to go into moles of NH3. So moles of NH3 ends up on top. That's going to leave us in moles of NH3. We now want to go back into grams because the problem asked us to be in grams, right? So grams of NH3. We're going to again use the molar mass. In this case, grams of NH3 are going to be on top because that's what we want to be in. We divide it by moles of NH3. Now I will point out that the only thing I have done in this chapter is I have given you 3 new units, right? That's it. It's just a dimensional analysis problem like we did in the first 4 chapters. Just a conversion, right? Okay. I've just given you 3 new conversion factors, right? Okay. Okay. So again, all of these problems you can always work out by just taking units and converting them over and over. Somebody is running around up there, and it is bouncing like crazy, isn't it? Hopefully nobody gets motion sickness. All right. So that gives me 39 grams of NH3 when I do that problem. Okay. Now, where did anybody get confused?
Okay, no, I do have a question. So,
Sure.
The 32 grams of I'll go to put that right there.
Mhm.
And then put that on top because it's going to cancel out.
Mhm.
The 28.02 we'll have to do up there.
Yes, you add the numbers from the N2.
And you have to take a gram of N2 and go to a mole.
That's what the molar masses are. So that's what those numbers up there, that's what they mean. They're grams per mole numbers.
And after that,
That's the mole to mole ratio. We got that from this right here. There's, for every one of these, you get 2 of these. Okay. And then this is just the molar mass of NH3. Again, from the periodic table.
that is where I'm confused. Find the NH3. So you have to find the N first, which is literally the 14 times
2.
2. Yes.
'Cause it's
And
N2.
then the H times 2. Is that a 3 or 2?
What do you mean by H?
The NH.
Okay, the NH, that's an NH3.
Okay.
So you take the 14 plus 3, which is the 17 here.
So you find you do 2 times 14 and then plus 3.
These are 2 separate things, 2 separate compounds. So you get the molar mass from the periodic table for that.
Yes, I got
You're done with that. No more times 2. Okay? Then you come over here and you do the molar mass for this. And that is 1 nitrogen, 14, plus 3 hydrogens, which gives you 17.
Okay.
And that's for 2 different compounds. Yeah.
Okay.
Not the same thing. Okay. Okay, so let's go and try this out. I'm going to make you guys do it. How many grams of O2 are needed to produce 45.8 grams of Fe2O3 in the following reaction? That first slide's actually the Q&A. It's for if you guys ask questions. I just skip them when there's no questions there. Okay. We'll get a slide up in just a bit for you to join. But you're going to need this formula here. Okay? So you'll want to write that down somewhere where you can work on it. So get that reaction there. Okay. All right, everybody ready? Got the reaction? You don't have to be ready to answer. It just
Okay.
you need the reaction.
I do have a question. Yes.
Yeah.
So we put the 45.8 on top, right?
Okay. Sure.
Okay.
Like you don't actually. There's like 5 different ways you can do this problem. It's math, so you can do many different ways.
You do over
Yeah. But yeah, typically if you want to go from something you already have, that's typically what you want put on top. Specifically because it's what you have. Okay, folks, there's the join information, there's the quiz. The numbers are still on here. The only part that's not on here is the reaction right now. Okay. Okay. So in this case, we're trying to figure out how many grams of O2 we need. That would produce 45.8 grams of Fe2O3 in that reaction, right? Okay. All right. And so what parts do you need for this? You need 2 molar masses, right? Okay. The molar mass of what? O2. And the molar mass of? Fe2O3. And then you need a mole-to-mole ratio from that reaction, don't you? Okay.
So we need the molar mass of 2 Fe2O3.
Yep, the Fe2O3 molar mass, and you're going to need the molar mass of... Huh?
I thought it was 2 Fe2.
That's done in the mole ratio.
Okay, so I don't. Okay, perfect.
So whenever you're doing the molar masses, keep in mind that you don't have to worry about coefficients when you do the molar masses. You just have to worry about the molar mass.
That's what was throwing me off.
The mole-to-mole ratio is the only place you have to deal with that ratio of moles in the reaction. Okay, folks, we're going to go ahead and go forward. Don't worry, just answer something if you haven't. And again, I'm going to have the workout after this. I mean, I'm just trying to gauge how many people actually are picking it up and can get the prom done so far. Okay? That's why there's homework. That's why there's office hours. That's why there's me working the proms out after these. Okay. Okay, folks. Oh, wow. That was really high. Okay, that was actually excellent. Wow. I wasn't expecting 94%. That's actually really good. Okay, so what we're going to do here is, again, we are trying to figure out how many grams of O2. That's what we need, right? And we have 45.8 grams of Fe2O3. Okay? So what this tells me is that I'm going to need to go from grams of Fe2O3 into grams of O2. I can't directly go grams to grams of any other number in a reaction, can I? Because these aren't multiples of grams numbers. These are multiples of moles numbers in this reaction. So to go from the Fe2O3 into the O2, I'm going to have to get into moles first. Then I'm going to have to use my mole ratio. Then I'm going to again have to go back to grams, aren't I? Okay? And that's my pathway. That's how do I get there. All right. So now I'm going to go ahead and generate the conversion factors I need. Okay? Because it's easier to talk about the conversion factors individually and get them set up and then flip them to what you need to do. Okay? Rather than having to do everything at once and making it really, really complicated because you're trying to do 5 steps at once, right? Okay, so we need a molar mass. We need that for Fe2O3. Okay, and so I wrote molar mass for this conversion of Fe2 to O3. And then I need a mole-to-mole ratio of Fe2O3 to O2, don't I? And then finally I need a molar mass of the oxygen, O2. All right, I'm going to do it. So I look up my periodic table. I look up iron. What's the mass of iron?
It's 55.845.
Yeah, 55.8. I'll just call it 56 for my writing up here, okay? Okay, and there's 2 of those there, so times 2. And then I add oxygens, which are 16 times 3, right?
Yeah.
That'll give me my molar mass of my Fe2O3 all together, which is 59.7. Okay. Okay, so this right here is my molar mass of the Fe2O3. Okay.
Why do you need that first? That's why I'm confused. I don't know where this is going. So,
Okay.
molar mass.
So this is how we convert back and forth between moles and grams.
So I need to remember like that. Right?
Yeah, that's why we did that. The problem is you're trying to do everything in one step, and this is something you gotta do in several steps, because otherwise you're gonna try to have 5 steps in your head all at once, and it's not gonna work out well for you. And so what we're doing here is that's that entire thing that I did first, and that's what you might want to start writing in a way that makes sense for you. Some people do this with arrows going into like a cloud. And so they would make a cloud then. I have 45.8 grams of Fe2O3. And they list out then I want question mark grams of O2. And then they would go, well, what things relate? I have this reaction here. The reaction relates moles to moles, right? We good with that so far? Hey folks, I'm having a lot of trouble trying to talk over you. Is it something that you wanted to ask or no? Okay. Okay, so the next thing I'm going to do here is I'm going to go grams. That's what I have here, right? This thing relates moles. So I need to somehow go from grams to moles. Okay. And so I write down, well, one of the first things I have to do is go from grams to moles for the Fe2O3. Okay. And then I write down, well, now I'm in moles of Fe2O3. Is that my final answer? No. And so I need to go into moles of O2. Okay. And how can I do that? A multimole factor or ratio. And then the next thing I do is, well, I'm now in moles of O2. Okay, I have so far traced my path to that. Well, moles of O2 are not what I actually want, are they? It asks me for grams of O2. And so I need to go from moles of O2 to grams of O2 here. Okay. And how do I do those? Going from moles to grams or grams to moles, molar mass. And so I've traced out a plan. The next thing I do is I go ahead and make those steps. I need molar masses, don't I? I need a multimole ratio, and I need another molar mass. Okay. And so I get the molar mass for Fe2O3 here. Then I'm going to get the multimole ratio. Okay. This is actually the wrong thing on here in terms of NH3 and stuff. Yeah. So I'm going O2 and Fe2O3. My ratio of those is there are 3 O2s equals 2 Fe2O3. Okay. All right, so if I want it in a conversion factor form, I need to go out of the Fe2O3 and into the O2. So I write the Fe2O3 on the bottom, because if I want to get out of something, that has to be on the bottom. If I want to go away from something, it has to get divided, right? And that's going to go into 3 O2s.
So we want to cancel off the 3 O2s.
No, you never cancel out the thing on the top.
Well, if it's on the other side side and the other one's on the bottom, you like cross it out, right?
So again, that the thing that you cancel out ends up being on the bottom if you're writing everything else on the top.
Okay.
Like if you write the 45.8 grams of Fe2O3, that means you're in Fe2O3s on the top, right? And that means to get rid of that, we have to have that on the bottom. Okay. And so what we're going to do next is we need the molar mass here. And so I look up at my periodic table, 2 times oxygen gives me 32 grams per mole. Okay. Okay, so the next thing I'm going to do is I have these conversion factors. I'm going to put them in together. Okay, this is where you can make decisions of what goes on top and the bottom, and you can always be right. All you got to do is cancel your units out, right? Okay, so we're starting with 45.8 grams of Fe2O3. This is why you always catch me whenever I'm like looking over your shoulder. Write out your units. Express what it's for, right? And hopefully you have a little Dr. Clausen in the back of your head saying that, okay? Write out your units. Express what they're for, okay? Uh-huh.
Wait, something just sort of struck at me here. I didn't realize this until now, but the numbers over on the other side, like the 45.8, when you were doing the math to find out the grams and the moles, that didn't even factor in. You were just doing the mass of the atoms. Do those numbers on the side not actually mean anything for the problem?
What do you mean, the numbers on the side?
Like the 45.8, when you were doing the stuff, find out the mass of the iron and the oxygen, you didn't even put those into consideration.
No, these were setting up these things. I was getting together those numbers. Yeah. So this entire process here, I'm just getting together the conversion factors I'm going to need later. Okay? So that I don't have to try to do it when I'm here. Because if I try to do it right here, then this turns into 15 steps I'm trying to do all at once. Right? And so if you're trying to go up the staircase, you don't try to leap from the top to the bottom or the bottom to the top, right? Yeah, hurt yourself. You take it, 1 or 2 steps at a time, right? Okay. And that's what I'm doing here. Okay, so I'm going to start with that 45.8 grams of Fe2O3. That's what I was started with in the problem, right? And that was what I was given. Okay. Now I'm going to go into moles because I know moles are what I need to actually trace things through a reaction. Okay? And so I take and I go into moles of Fe2O3 and I put on the bottom the grams of Fe2O3. That ratio right there, that's that molar mass that I figured out. Okay? Okay, so the next one I'm going to use is the mole-to-mole ratio. This one's going to have to go into O2 because that's what I actually want out of my problem, isn't it? At the end of this, I want to get into O2. And so that is the mole-to-mole ratio. 3 moles of O2 are from 2 moles of Fe2O3. Okay. This doesn't have anything.
2 grams of O2 by multiplying that by 2, 15.999.
Yeah, so 15.999 would be 16, right? Times 2 would be the 32 right
Okay,
here.
I just want to make sure. Okay.
Yeah. Okay, and so my next step is going to be using the molar mass for the O2 because the end of this, I actually want grams of O2, not moles of O2. Now again, how do I always figure out what I'm going to be in and which one needs to be in the bottom? I always just go through and I cancel things out, right? So here I have grams, those cancel, see that? And then on Fe2O3s, they cancel, that leaves me moles of Fe2O3. The next thing I go is I need to cancel out moles of Fe2O3s. That leaves me in moles of O2. And see how I just methodically cancel things out. Notice that's that same steps we had been doing for chapters 1 through 4. We're just adding new types of units, aren't we?
Yeah.
Okay, and so we go ahead and cancel moles of O2. And that's going to leave us in grams of O2. Everybody good with that part? Fantastic. That's always how I figure out what needs to be on top, what needs to be on bottom, right? Is I always double check my units canceling. If I'm left with the proper units on top, it's okay. I've done it right. If I'm left with the wrong units on top, what do? yeah, I go back through and see where I messed up. Where did things not cancel? Okay. And I flip those things around. Okay, so we're going to go ahead and try this one right here. The reaction between the O2 and H2 and O2 produces 13.1 grams of water. How many grams of O2 reacted? Okay, so everybody should try this out. Devin,
Yes.
make sure you try it out. This is how you guys will actually find out where you're having issues. What you should always do for these problems is you should always work them out as much as you can. And then where you go off rails, you can see how I worked it, compare, and then that'll tell you where your issue is. If you didn't get particularly far the first time, you can always go back, look at the first slide only, try to work it out again, and then see how I worked it out and see where you went off the rails the second time. Okay. And you can keep doing that until you're right, and you do it right. Okay. Okay, and so we were given the 13.1 grams of H2O, right? And we need the grams of O2. So we're going to go grams to moles, do the mole ratio, and then we're going to go moles to gram, aren't we? Okay. And visually, in case it helps you, that's what that looks like. Mm-hmm.
So you start with the 13.1 on top. Okay.
Yeah. Yeah.
Just want to make sure. Never done any of these ever in my whole life. So,
I mean, they're just conversions.
yeah, I've never done conversions.
You most definitely did conversions with me.
Oh, yes, you do. But before that, no, never.
That's true.
Never had magnetic labels.
Which again says a lot about the sad state of the world, not me.
Well, I figured like this generation's a little younger than like, okay, I'm 10 years older than most of the people in here. And I have,
Oh no, they still make magnetic Legos.
they're hard to find.
Never.
Yeah, they gotten kind of cheap.
Yeah.
Lego has. Yeah.
So, okay, the second step, you have to take the hydrogen, bind it up there, and times it by 2, correct?
Okay, so we're going to go through this now. We're going to take the 13.1 grams of water, right? And we're going to need the molar mass of water to convert that to moles. That'll be the first thing we do. The next thing we're going to do is we're going to take the mole to mole factor or ratio of H2O to O2. And that's going to just be this ratio between these two right here. So it'll be a 2-to-1 ratio. The next thing is we're going to then take the moles of O2 going to grams. That is going to be the molar mass again, right? Okay. Now we're going to use things for H2O, and we're going to use things for O2, right? The one we don't actually care about or need anything to having to do is the H2. That one is not actually useful for this problem. Okay, so the next thing we're going to do here is we're going to take the molar mass of H2O from the periodic table. Again, that's 16 plus 2, right? 18 grams per mole. We're going to take the molar mass for oxygen off the periodic table. So oxygen is 16. There's 2 oxygens in that formula. and so that is 32. The mole-to-mole ratio is going to be that 102 from, again, this right here is 2 moles of H2O here. Okay.
Wait a minute. Okay.
Mm-hmm.
1802. Where did that even come from? Because 8, that's 1 times 2 is 2, and then 1 O is only like.
Is 16.
Okay, so you round it.
Yeah. Well, this isn't actually rounded. This is if you add those
No,
together.
32. It's not 18.
No, it isn't. 2 times 1 is 2,
Yes.
and then you have plus 16.
Oh, so you add. Okay, 18 plus 2. Wait.
Okay.
I have no idea.
Okay. Anyways, we can talk about that. That's math.
Oh wait, never mind.
Okay. Okay. So we're going to take that 13.1 grams of H2O. This is then going to be divided by that molar mass of H2O, that 18 grams per 1 mole. Okay. Notice again our units canceling. That's how you always want to do these problems, as simply dimensional analysis conversions where you cancel your units off. Okay. Then we take that mole ratio. The water goes on bottom because we were in water. We want to get out of water. We want to go to oxygen. Okay. And then the next step is we're going to get back in grams for O2 this time. And so we're going to take the moles on bottom because we were in moles, go into grams on top. Okay. Again, this is the grams of H2O right there, 13.1. This right here is the molar mass.
How do you know to put the 1 mole on top and then over 2 moles of H2O?
It's canceling units.
Okay.
So here we have H2O
That.
on the top right there.
Okay. Okay.
Okay, and we want to get rid of H2O to get to O2.
Okay.
If the H2O had been on top, we would not have gotten rid of H2O, right?
Okay. Yeah.
Okay. So let's talk about some chemical energy and reactions. This is actually usually the part that people are more interested in. So the high temperature of a thermite reaction, for example, has been used to cut or weld railroad tracks. It's been used for many different purposes. It's used to disable tanks. It's one of the ways infantry can actually disable a tank. And actually, modern day munitions oftentimes use thermite reactions in them. Typically, like a vehicle destroying munition. So, 3 conditions for a reaction to occur are the following. You need a collision. If they don't collide and come together, you can't get a reaction, right? Okay. It's kind of like, can you high-five somebody if they're across the building? No. Can't shake their hand either, can you? Orientation. The reactions must align properly to break and form bonds. How easy is it to shake somebody's hand if you're facing back-to-back? Not going to work as well, right? Yeah. And finally, the energy. The collision must provide the energy for an activation. So if 2 things hit each other, but they don't have enough energy behind them, they're just going to bounce off each other, right? It doesn't matter if you have enough the right orientation, and they could. It doesn't really matter if they do collide. You don't have enough energy to actually get together. Okay? And remember that most collisions for molecules, if you don't have enough energy, are actually just going to be their electrons repelling each other, right? They will never actually come nucleus anywhere near the electrons. Okay? Okay, this is again referred to the energy of activation. You can think of it a bit like when you go to a theme park. Everybody okay with this park being Disney?
Yeah.
Okay. We go to Disney. What's the first thing that has to happen to actually do anything with Disney at all? You got to get through the gate. You got to pay for the gate, right? Okay. And this would be the fee you pay for the gate. Okay? If you get in the correct orientation and you get to the ride, then you could actually, get onto the ride. But you got to pay the gate fee first, don't you? Okay? So this is going to be an exothermic reaction. Exothermic reactions are where heat is released. Okay? This is things like combustion, where heat is being released into the surroundings. You know them because they warm you, because you're almost always the surroundings. Okay? The energy of the products is going to be less than the energy of the reactants. That's why they're giving off heat, is because the energy that's within them is going down. Another way of saying this is they are spent fuel, right? Okay. This is actually an example of this. That is the carbon plus hydrogen. This is an endothermic reaction. You guys haven't probably experienced as many endothermic reactions. They're relatively rare around you. But anybody ever seen one of those breaking cool packs? Where like you can crunch them up and they cool in your hands? That would be an endothermic reaction. Okay? Not as common as exothermic though, right? Like, there's exothermic everywhere around you. Endothermic is actually fairly rare for you to see. Your sweat drying on you is actually an endothermic reaction as well. But it's just a phase change, so it's not very impressive. Yeah. So, in an endothermic reaction, we're going to absorb heat from the surroundings. That heat is going to go into the molecules that are being produced, making them higher energy molecules. You can think of it as energy going into the system to bring them up stages. Okay? And that is an example right here. This is actually the Haber reaction. It's kind of a fascinating reaction. Also the reaction you'd see in like a car. Yeah. So when your car's running, it produces a little bit of NO, which is what produces smog eventually. Okay? And that's why like California has pretty bad smog problems. Well, it did. It's not as bad anymore. Okay, so identify each reaction as exothermic or endothermic. The big key you want here is, where is the heat? Is the heat being produced where it would be on the what side? Products, right? Or is the heat getting consumed? If it's being consumed, that's on the what side? Reactants. So, exothermic is heat being produced. And so the first one, is it endothermic or exothermic? Exothermic, exactly. The next one, is that endothermic or exothermic? Endo. And then the next one is exo. You got it. Now, one of the things I would like to point out here at this time is that there are stages to chemistry, right? And stages to classes. Okay? So there's a level of knowledge that you need to interact with the questions, and will get you a certain degree level of grade, right? In chemistry, for these chapters we've covered so far, and for the remaining chapters, that level is mostly terminology and understanding, right? Now, I can only give you so many questions on math, right? In an exam. The majority of the questions are going to need to be terminology questions. So as a strategy, you can actually understand strategically that you do not fail an exam from 4 out of 30 questions, do you? That's not a failure. If you get 1 or 2 questions wrong, you've actually done really well, haven't you? Okay. If I can only ask, because of time limitations, 4 or so questions or 1 or question on each topic, then you cannot master one topic and you will be fine, won't you? Okay. The topics, knowing this as being a strategy and knowing you guys have limited time and you're probably not going to give my class, this general education chemistry course, the majority of your study time in college, I am going to state that I have had multiple people try to cheat on my exams. The people that try to cheat on my exams always fail. The reason for that is the key to unlocking chemistry questions, as you even being able to guess on them, is terminology. Okay? If you have the terminology, you have the concepts, you can interact with the questions, right? If you don't even have that, which is what most people that try to cheat on chemistry exams that don't have, then even if you ask somebody, you won't understand the answer and you won't understand how to ask, right? Okay. So let's talk about the reaction rate real quick. The reaction rate is going to be, are these collisions meaningful? How much of these collisions are happening? So this can be a speed at which the reactant is used up. This is the speed at which the product forms. It's going to increase when the temperature rises because the reaction molecules move faster, providing more collisions between molecules that will have the energy you need to activate them. Okay? And so more of those collisions are going to be meaningful, and there's going to be more collisions. It'll increase with increasing concentrations. Catalyst is going to be something that increases the rate of a reaction. It's not going to increase whether the reaction happens or not. It's only going to make the reaction faster. Okay? You may have heard of catalysts. Has anybody heard of enzymes? Yeah?
That's right.
Those are catalysts. Okay? It'll lower the energy of activation. Remember that energy of activation, that energy you have to overcome for a collision to be meaningful? It's going to lower that energy. Okay? It's not used up during the reaction. That's a key factor for a catalyst and an enzyme. They're not used up in the reactions. Those are those factors. Okay. I'm going to skip the questions so we can actually cover the thing. Ask me questions if you don't understand something, okay? Okay. Okay. Oh, that's done. Do you guys want to try these questions real quick?
Sure.
Okay. So let's indicate the factor. You can actually leave after you've done this, okay? So we'll do it quick. Indicate the effect of each factor listed on the rate of the following reaction as an increase, decrease, or no change. So keep that reaction in mind. Raising the temperature. So lowering the temperature, is that going to increase, decrease, or no change for that reaction? Lowering the temperature.
Can you bring it back up? It throws me off for some reason.
Okay. So if we lower the temperature, what does that do for the speed of that reaction?
Can you show the formula again?
It doesn't matter, actually.
Doesn't.
No, not for this one.
No, then I'm going to say no change.
Okay. And that is going to indeed decrease the speed of a reaction if you lower the temperature.
All right.
Think of baking. If I bake something at a lower temperature, it's going to go slower, right?
Yeah.
Yeah. That's exactly, baking is reactions, right? Okay. What the hell? Oh, wow. My question's all, that sucks.
What happened?
All three of them are the same question.
Yeah, it, when I put them in, it messed up my order. Yeah.
Like catalyst with increase because it's raising the activation energy.
Catalyst increases it, exactly. Makes it faster. Increased temperature makes it faster. Adding O2, adding a reactant, would make it faster.
Yeah. Just about everything makes it faster except for lowering the
Exactly. Yeah. You all have a wonderful day. I'll see you Tuesday. What are we doing Tuesday?
Test.
Okay, everybody with me? We are doing what on Tuesday? Test. Okay. Can you use notes?
Yes.
Yes. Okay.
and your neighbor. That's why I said my note.
Nope. Unfortunately.
Dr. Washington, I have a Zoom scheduled with you today.
Fantastic. I will see you on the